Hello everyone and welcome to my YouTube channel Study with Dani. My name is Daniel Lottery and I'm excited to have you here. If you are new here, kindly subscribe to the channel and click on the post notification bell icon so that you don't miss any new video. From the title, I guess you already know what this video is about, so let's get right into it. In order to have a full understanding of this tutorial, it's advised that you watch part 1 of this video, which is provided in the link above. I think we can start now.
Yes, Dr. okay.
Sorry?
So we are with you.
Okay, all right, thank you. Okay, so in the first part, I actually took you through the data pre-processing and feature selection models. Now we are moving straight into making our first machine learning model predictions. So I'm going to use three major types of machine learning models, which is the ridge regression, which is more or less a linear model. I'm going to use an ensemble model called the bargain. And I'm going to use the extra tree model, which is also an ensemble model, but it's developed from the decision trees model. And I'm going to use the extreme gradient boosting regressor. But before we do that, we have to import our statistical metrics, which we will use to evaluate our model. So we have to import sklearn, since most of our models are from the sklearn library. So from sklearn, we have to import our metrics. And then from sklearn.metrics, we have to import the mean absolute error. Okay. Let me just copy and paste this. We also have to import the R-squared score from sklearn.metrics. We also have to import the mean squared error. And then from maths, so there's a library called math, we have to import the square root. And we will use this to calculate the root mean squared error. Okay, so we've imported our library. If there's an error, the code will tell that there's an error. Like, for example, you see it's telling us that this is not found within the library of maths. So if there's an error, it will point you to where your error is, and then you can go inside and correct it. Okay, so like I said, we are going to use the ridge regression. This is the code to import the ridge regression. And now I assume that everyone knows how to train their model. Okay, so you have to assign your model a name. So I'm going to assign mine as ridge. Then I'm going to say set it as ridge. So this ridge, and you open bracket. All right. So I'm going to say my ridge, which is this variable, which has been set to the model, okay, should fit my train data, which is our input train data and output train data. So the model is going to look at this data and try and learn from it. How does the X train predict Y train? And you remember X train is all of these variables minus sun flag, saturation, caliper, and shear sonic. Okay, so that's your X train, and your Y train is your permeability log. So what this model is saying, or what this code is saying, is fit yourself to this data, which is about 1,806 data points, and learn from it. Now that you are done learning, I want you to make predictions. So I'll assign the predictions as Y ridge, and I'll say ridge, which is this, right? Ridge.predict. So this is what you use to make predictions. So once your model is done training, predict. and we use the X test, which we haven't used to train the data. So X test is 319 data points. Okay, so from X test, predict Y test or predict Y range. Okay, so now we have Y train, Y test, and Y range. Okay, so let me run these two codes. So Y train is what the model has been trained with. Y range is what the model has predicted. But Y test is data that the model hasn't seen. Okay, so we would then compare the model predictions to the Y test. And how do we do that? There are a set of codes that we use in order to show how the model performed. So I am setting mine to score train. So I'm just saying, tell me how accurate the model was in learning from the data that I asked it to learn from. All right, then the next point, I am going to ask it to tell me, there's a test. How did the model perform when it predicted Y range? So it's just going to compare X test, Y test. But it's going to say from X test, it predicted Y range. So to compare Y range to Y test. Then again, I want to know my mean absolute error. Okay, so we are going to use metrics. Remember, we imported mean absolute error. So metrics.mean absolute error. And we are going to compare Y test to Y range. Okay. Then we want to know our mean squared error. So let me just copy and paste this. Because it's the same thing, you just have to change this to mean squared error. And then from the mean squared error, we want to get our root mean squared error. So we will say numpy square root of this mean squared error. Just copy and paste it. And then I want to find the mean absolute percent error. You don't really need all of these error metrics, okay? But sometimes it's important to see how your model performs by using different error metrics. Y test against Y range. Okay, so now that we've entered this, we want to print it. If you don't print it, you will not see the result. So you have to use the code print, and then I'm telling it to print by use this accuracy of train data. Show me this result. Okay, so let me just run this to show you. So it's just showing this result, but we want to show all of this result, okay? So let me write all the codes, accuracy of test data. Okay, and then, so we say this is mean absolute error. Then show me this result. And then root mean squared error. sorry. And then this one. So root mean squared error, mean absolute percentage error. So when you run it, that's giving you all the metrics that you want. Okay, and you can realize that the accuracy of your trained data is very, very low. As such, the predictions was really poor. This is what we call underfitting, because the model didn't fit our data very well. If, let's say, the accuracy was above 0.8, we would say it's a robust fit. But then, because the accuracy is very, very low, we say this is an underfitting. And underfitting is poor. We have overfitting also, which is not desirable, because that one fits to all the noise within the data. If you get a train accuracy of, let's say, 0.8, and you get a test accuracy of 0.75, that's a robust fit. But if you get, let's say, train accuracy of 0.8 and a test accuracy of 0.3, that's an overfitting, which is really, really poor. There's also another error metric that is important when you are comparing two or more models. And I call this the AIC, which is the Akai Key Information Criterion. So in order for you to probably, in your research, in your publications, you have to show this metric, which tries to tell us if your model has a higher probability of fitting new data set or not. So how this one works is the lower the AIC, the higher the model's probability of fitting, which is actually good. So when you compare all the results, like the AIC result for all the models, the lowest one is actually good. That shows us that the lowest one has the ability of fitting new data. So it's dot fit. All right, so this is giving us an AIC of 4571. At this point, we don't know whether it is good or not, but from the accuracy, we can tell, and from the error metrics, we can tell that this is really, really high. Okay, so let's go to the Bargain model. So we have to import Bargain as Bargain regressor. And if we are going to assign it to a variable called bag, we are going to say Bargain regressor to bracket, and we are going to train it as bag.fit into bracket our X train, Y train. So we've done our first machine learning model predictions. We are going to do the next one, and then we will compare the results. So we name this Y bag, and we say bag dot predict, because we want it to predict using the same X test data. So we run it. Now the model is done training. You see how fast it is? It's done training. And we entered the same data from here. Okay. So what this is, okay, I didn't add this one. All right. So what this is doing is you just have to name these ones differently. So replace all the range with bag and replace Y range with Y bag. So you can just do copy and paste, replace all the range with bag and replace Y range with Y bag. So as you can see, we have a train accuracy of 0.99, which is almost 1, which actually shows that the model does well in training or in fitting the data. And when it's predicting, it's also 0.988, which is also really high. This shows a robust fit when you use it to predict permeability, while giving us mean absolute error of 5 millidarcies. You know, permeabilities above 10 is actually okay, and permeabilities above 20, 25, 50 to 100 are actually what is desirable. So having a difference of 5.6 millidarcies isn't really much. And in terms of the mean absolute percentage error. It's actually less than 10%, which is actually really good and what we want the model to do. And in AIC, it's giving us 3,161 as compared to 4,571. Okay, so the next model that we are going to use is also the extra tree. And this follows the same pattern. Okay, so from sklearn dot ensemble, because it's an ensemble model, import extra trees regressor. So let me just copy this. So I'll name the model as extra, and then I paste this, then extra dot fit. Let me just copy this one. And then bring this one. So how will I name this? I have to change bag to extra. And Y bag, I'm going to make it Y extra. So I run to import the model, I train the model, and I fit the model. And as you can see, this was 0.99, 0.988, or let's say 0.99 also. And the error was 5.6 for the mean absolute error, and the percentage is 8.7. But when you look at this, the error is really low, okay, and the percentage error has really reduced. So what this is telling us is that the extra tree is a better model than the bagging regressor when we use it to predict permeability, because the percentage error is less than 8% as compared to the other one. And the AIC is 2,551, which is about 600 points lower. And the lower the AIC, the better. Okay, so we are going to go to the next model, extreme gradient boosting, which is normally used in making machine learning predictions because it usually works great with small data and large data, highly dimensional data or low dimensional data. So normally, if you don't have it installed, you have to input this code to install the model because the model isn't saved in sklearn. Okay, so once you install the model, then you go to, I've already installed it, so I'm not going to run it. XGBoost.sklearn import XGB regressor. So it's basically going to be the same thing. So this is just to show that the machine learning model training is actually simple. It's nothing confusing. You just need to assign your variables correctly. That's all it is. Okay, so now I'm going to make predictions. So I'll name mine YXGB. And then I'll say XGB dot predict to make predictions. So it has also finished running, and let's see the metrics that it's showing. So what this is showing us is an mean absolute error of 3.81 and a mean absolute percent error of 12. Okay, and it shows the AIC of 2853. Based on the results, it is clear that the extra tree is the best model in making predictions. So at this point, we can end your machine learning journey, but that is not really the end of it. What you need to do is you need to visualize your data and understand what result you are actually getting. Right, so XGB also has a feature importance too, which will show you that it's actually made its prediction using a density corrected more, the gamma ray and the T. However, we know that density correction does not have some, like, it doesn't really correlate to permeability. As such, I would say, based on this, which you can add it to your discussion, that this log that XGB focused on the most added to its having a higher error of above 10%, although the train and test accuracy is 0.99, which is really good. People normally just focus on this and then just say, oh, my model is good. No, you have to understand how your model made the predictions. And because XGBoost focus on this log. I would say the XGBoost isn't really that accurate, but let's see. Let's see if when we visualize the data, will extra tree, will bargain, or XGBoost be the best? Because as it stands now, the worst is the ridge, the second worst is XGB, then bargain, then extra tree. So this is a code to tabulate your results. Okay, it's actually simple. You can go through it. It's just you creating a data frame. You create your first column and you put in the names. You create your second column and you put in the values that you want, which is the train data and so on. So let me just run it to show you. So I've created a table from the results, and from the table, we can easily compare results to know which one is the highest or which one is the best. And we can see that the extra tree, in terms of all the error metrics, is actually the best. One nice thing about creating a table of your results is you can actually save the table as a CSV or Excel file. Okay, so I'm going to save it as summary. I use PD for pandas data frame, and I'm going to say save the summary file. Okay, and then I'm telling it to save it as CSV file format, and then save it as a summary predictions.csv, index equals false. Okay, so once you run this, it is saved in your folder. So you can see the time that I have saved this, summary predictions. Okay, so you can always open and then view your data in Excel, and you can make your own plots in Excel if probably you feel that you don't want to use the Python again to make predictions. So you can just use Excel to make your predictions. All right, let me just use this one. Insert. Yeah. So you can just use Excel to make your predictions. Something like this. Then you can insert it to your report. But I would prefer to use the models or Python to make my predictions. So right now that we've saved the result, let's save the predictions that each model made also as a table. Okay, so pd.dataframe. We are doing this so that we will have an Excel file of what the model predicted. Okay, so pd.dataframe test. Now we want the actual data. So within this column, I want my actual data of my test, which is y test. Okay, then the table name is test. I want ridge predictions. Sorry, I think I made a mistake here. So ridge predictions, I want it to be y ridge. And then we do the same for the rest. ET predictions for extra tree. We set it as y extra. Let me just copy and paste to make it faster. So ET predictions, and this is XGB predictions was XGB, and then bargain was y bag. Oh, and remember I set sand flag because I want to show something. Sand flag as sand flag because I want to use it as part of my result. So test. So what this is showing us is for the sun flags, okay, and the model prediction. So this is going to help us to see this model is predicting 109, which is over predicting. So mostly you can see that this over predicts the range predictions are actually over predictions. And then when you focus, the extra tree is supposed to be the best, right? But when you look at it, the bargain predicts more better than the extra tree. And when the actual or the test data was 0.00 millidarcies, the sun flag is showing that this is a non-reservoir interval or a shear interval. So we don't expect the models to predict high permeability values. So this is one way of also analyzing your results. Okay. And another thing to realize is the XGBoost makes negative predictions. We don't have negative permeability results, so the best thing to do is to change it to 0, or you just use Excel to negate it. So what we are going to do is I'm going to save this table, pd.data frame. This was saved as test. I'm going to save it as an Excel file. And I'm going to name it model predictions.csv index false. Index false will remove any index which is 0, 1, 2, 3, something like this. It will remove it from the data. So I've saved my data and you can visualize it here. Okay. Okay, so right now we are going to visualize our data, and I'm going to use the kernel density estimate. Okay, so I think for the sake of time, I will not focus so much on the code. I will just take you through it. Okay. So you first have to set a subplot because I am going to plot two different results on one graph. So you need to set plt.subplot. And what I'm going to do is I'm going to show the first predictions as the predicted range value. So I'm going to use the range predictions. Okay, so I saved it as range predictions. Okay, now let's see what it gives us. So this is showing us that when we have 0 actual permeability data, the yellow is the actual and the blue is the model predictions. There's actually an under prediction because it doesn't really predict as high as it should, and it's slightly off because the shape doesn't even match the actual one. Now let's see that of extra tree, which is supposed to be the best. You can see that the extra tree overlaps the model perfectly. And even when you look at high-end permeability result, it actually overlaps it almost perfectly. Remember, the error is it's less than 3%. I was around 2.3%. Now let's look at the XGB. The XGB also slightly under predicts because it was predicting negatives. But then high values, the XGB also seems perfect. And then we look at the bargain. And the bargain is also showing excellent results, but there's some small discrepancy when we get here. So I'm just focusing on these ones and I'll select the best ones. I didn't use the sun flag yet, but I'll use the best ones in the next result. So you can actually show this result in your final year project and also in your publications. All right, so the next one is the joint plot. So for the joint plot, we have to set the figure because we are going to show it as a figure. So you have to set the figure and use SNS.joint plot. and we have to set our X value. So on the X scale bar, we want to say XGB underscore predictions. And then our Y should be the actual. And then the data set to use, the data set to use is going to be the test data, which we've already saved. And what kind of graph do I want? I want the reg or regressional plot. And then what color? I want the color to be blue. Okay, and then PLT GCA. So this is just the code to save your data. Okay, so sorry, I think I would not use the XGB. I rather use the bargain. And let me just check how I saved it. Bargain predictions. And I'm not going to use the range because I know that the range isn't really that great. Okay, so when you run it, okay, there's an error here. Right. So this is it. Okay. It's also telling me that there's an error, the X bargain predictions. Okay, so you see, I made an error and the model just told me where my error is. So I had to just go in and correct it. Let's give it a few seconds. It will be done running. And for the, whilst we are waiting, I'll also run the next lines of code, which will plot the joint plot for the XGB and the extra tree model. Because from this result, it is the bargain, the XGB, and the extra tree that shows promising result. So we are going to focus on those three. So let's just give it some few seconds. Whilst it's running, are there any questions? No questions? Okay, so let me just quickly run through. So what this is showing us is a plot which shows 95% confidence interval. And this result actually tells us a lot. Although when you look at the result, it shows that at high predictions, the model is really good and it overlaps. This shaded area shows us the uncertainty region. And this proves that at high values of around 500 millidarcies of permeability, there's a high uncertainty when you use the bargain model, and it mostly underpredicts for high intervals. And this will be a problem in terms of reservoir characterization. When you look at the XGB, it actually shows us that at about 1,500 millidarcies, there are some error or under prediction, mostly in high intervals. But this isn't really much of a worry because 1,500 millidarcies in terms of permeability is actually high in itself. Okay, so when you compare this, although bargain, let me just quickly show this. Although bargain gave the error percentage of 8, and it showed like less error percentage than XGB, it had other metrics higher than the XGB. So in order to confirm that the XGB is actually better, you can use the visualization to actually show it. And then when it comes to the extra tree also, it kind of looks similar to the XGB, but then I would say that the XGB kind of show a better accuracy when it comes to high values than the extra tree model. Okay, now let's use another plot to also visualize and see if actually the XGB is better than the extra tree. So I'll just copy and paste this just to save time. And then this is going to be extra tree. All right, so I am going to show it in terms of sand interval, like the reservoir interval and non-reservoir interval. Okay, so this will give us an idea as to which of them is actually accurate in terms of reservoir interval and non-reservoir interval. So sand flag not in index. Dataset test. Oh, sorry. I think I didn't name it correctly. And the same for this. So what this is showing us is when it comes to predicting for non-reservoir intervals, the extra tree is really accurate. But when it comes to predicting for the sandstone intervals or the reservoir intervals, the extra tree shows high uncertainty. And if you see the shaded area and you compare it to this one, the XGB is actually very accurate in the reservoir interval. But when you look at the blue line, which is the non-reservoir interval, it is less accurate. But we are actually looking at the model that will give us better predictions in terms of reservoir intervals. Okay, so based on this result, I would say it is better to use the XGB model. Although the SRG model gave excellent results, less error, looking at the visuals, how I will go with the XGB model because it gives me higher accuracy, less error in terms of reservoir interval predictions. But you can also argue that the reservoir interval can have a mixture of shales and sandstones. So you may want to go with this. But if you have a homogeneous sandstone reservoir interval, you have to go with the XGB model. Okay, so after my results, now what I want to do is I want to train the model, which is the XGB model, which I have chosen as my best model on all the data sets. You remember we divided the training into test and training data set. Now I'm combining all the test and training data sets, okay, to train the model so that the model will be trained on all the data just to make sure that the model has enough data to learn. So I'll still remove the data that random forest said are not important. Okay, so x.drop, and this is my new x. Okay, so now I have trained the XGB model on all my data sets, including the test data. What I'm going to do is I'm going to deploy it on a new well. Okay, I'm going to deploy it on a new well. So I'm going to name my new well as deploy pd.read because I need to read the data from somewhere. And I'll use R to read, and I have to go and copy my deploy data, which is this one, copy as path, and then paste it here. Okay. Oh, sorry, I made a mistake. And then I want to show my deploy data. This is actually a new well, so I want to make predictions. It doesn't have a permeability log, but I want to make predictions. So this is the beauty of machine learning. You've trained the model to predict permeability. Now you have a well that does not have permeability. So you can use your model to make predictions. And in this one also, we will set the depth as our index, like we did before. And so you set the depth as our index like we did before. And then the next thing that we have to do before we make predictions is to define our input and target. So from the deployed data, we are going to drop these data. this is what we are going to drop, because extra random forest says we don't need this. Okay, so from here, we are going to print the number of, let's say, samples. Okay, and we are going to show it as x.shape. And flag. Okay, so DTS is not found. Okay, so it's telling us that it doesn't have DTS. So yeah, so you have to delete DTS because you don't have DTS in this well. So this is showing us 11,935 data points, which is even more than what we use to train the model, which is around 2,000 data points. So we use 2,000 data points to train the model, and we have almost 12,000 data points to make predictions for. So let's see how our model will perform. Okay, so let's say our new model or our new predictions, XGBoost. That is short form of predictions. XGB is the model. We want to make predictions, so dot predict on X, because X have the target. We don't have permeability. We only have the input data. So we are making predictions. Okay, sorry, I had to put it offline. Feature shape mismatch. 13, expected 13 got 10. Okay, so I think I made an error here somewhere. Just a second. XGB new. So that is it. Just a second. Let me retrain the model. I think I made an error somewhere. So when you get an error that, let's say you try to fix, but it's not possible, you have to go back. Like even when I run this used to work. Even when I run this, it's not working. So we have to go back to where you think the error is coming from. Okay, so you import the data again. And then you try and find out where the error is coming from. Now let's see. Okay, now this is working. So let me try and train my XGBoost again. Yeah, this is working. And then try and retrain all the data again. Okay. So we've deployed the model. So it's expecting 13, it got 10. Okay, I know what the problem is. Okay, so I'm going to use a different data because it means that there are some logs that are not in this deployment data. So that is why it's not really working. So I'm going to change the data that I'm using. It doesn't have all the input logs. So yeah, you can see this has 18 columns, but the previous one had 14 columns. So obviously it didn't have all the input data. So I'll just run the same code. And then I'll try and remove, this one has DTS, so I'll remove DTS from it. And then I'll make predictions. Great. So now it's working. So always, if your model requires 13 columns, you need to give it 13 columns. If you give it 14 or less, it will not work for you. Okay, so now that I've made my deployment, I'm going to add it to my data. So predicted KLOGH is equal to XGB spread, and I'm going to visualize it as deploy. Sorry, I need to add. So when you look at this data, it did not have the permeability log, okay? But now the model has predicted and it has the permeability log. Although it's predicting negative, like I said earlier, XGBoost was predicting negative, so you can zero this one out, okay? So this is a function to use to zero out all the negative predictions. So deploy.log. So on the deployed data, within the predicted KLOH column, any value less than 0, create another column. And make it 0. So all the negative data will be changed. So let me just, so I'm going to show the first 20 rows. Okay. So when you look at this, everything is now zeroed out. All the negatives is all now 0. Okay. So this is also one fancy way of creating your table. I think this just helps to make your data nice by showing where the high values are and the low values are. So once you are scrolling through, you realize that this is a high permeability interval, and you can see that it matches with the sand flag, which will tell us that this is actually our reservoir interval. Okay, and you can see high porosity also. So this is a fancy way, but it also helps you to analyze your reservoir well and see whether you have your predictions are actually in the right places. And this is how to visualize your wireline logs without using Petrel. I'm actually working on this, and I'll release it as maybe a Python library so that anyone can use it to make predictions, and they can actually visualize their walls without having Petrel. So this is showing us our logs and our predicted permeability. And as we can see, high permeability matches with high porosity, and it matches with low water saturation, and it also matches with low gamma ray. So from here you can see the reservoir interval, and it matches with high permeability, high porosity. So this shows us that the model is actually working great, and the model predictions can be trusted. Okay, and you can simply use this code to save your data as an Excel file, so that you can visualize your predicted data. So this is it. You can visualize your predicted data. Right, so this brings us to the end of your machine learning predictions for beginners. I hope that with this tutorials, you were able to learn a lot. To recap and to focus on what I expected you to take out from this, I expected that you'll be able to import your data and your libraries into Python. I expect that you'll be able to clean, visualize, and analyze your data to understand it and make your own analysis out of it. You'll be able to perform simple feature selection using Spearman and random forest. Then you'll be able to train and test your machine learning models, as well as evaluate your model performances using statistical metrics like the mean absolute error, root mean squared error, and the charts like the kernel density and the joint plot and the line plot. Thank you very much for staying with me up to the end of this video. If you like this video, give it a thumbs up, subscribe to the channel, and share with your friends. If you have any question or topic that you'd like help with in learning, leave it down in the comment section and I'll try my best to attend to it. Click on the post notification bell icon so that you'll be alerted whenever a new video is uploaded. Here at Study with Dani, we teach in order to learn and we learn in order to teach. Stay safe. Bye-bye.